I am Eugene Kim, MBN announcer and the moderator for this session.
오픈 세션
We'll now begin World Knowledge Forum's open session, Science Concert, Turning Dreams into Reality. This session was jointly prepared with the Institute for Basic Science. The Institute for Basic Science is the first research institute dedicated to basic science in Korea, established to research basic science to prepare future generations. As of now, chemistry, convergence, and bioengineering and other 31 research groups are being established. This concert is to commemorate the 10th anniversary of the Institute and was prepared as a platform to introduce the lives of representative scientists of IBS who are heading for new discoveries and stories of science. So we wanted to invite many people, but unfortunately we had to choose to meet online. There are many of you watching this open session, I believe, and I hope you will stay with us until the end and hope you enjoy it. I will then invite the first speaker, Axel Timberman, who is the head of the Center for Climate Physics at the Institute for Basic Science. Director Timberman became the head of the Center for Climate Physics at the Institute for Basic Science in 2017 and is currently the chair professor at Busan National University. In 2018, 19, and 2020, he was selected as the world's most influential researcher by Collaborate Analytics. And in recognition of his contribution to disseminating climate research to the general public, he received the Scientist of the Year award by the Korea Science Journalists Association. Please welcome Director Timberman with a big round of applause.
Good morning, everybody, from Hanul Theater in Seoul, South Korea. Terra Incognita, the unknown Earth. Today, I would like to talk about one aspect of this unknown Earth, and that is our climate system. My name is Axel Timmermann, and I'm the director of the IBS Center for Climate Physics at Busan National University. When I founded the center, when we launched the center in 2017, I was excited. I felt like this is a new opportunity to fulfill, to realize dreams, explore new adventures, and embark on a new journey of discoveries. So it's about a journey today. I will talk about my journey, a bit a personal journey, and it's about passions, dreams, discoveries, and adventures. Well, I have three passions in my life. Well, at least three passions. One is music, piano playing, and even though this session is called Science Concert, I won't play any music here today. And the other passion that I have is hiking. And I won't be talking about hiking trails on Molokai and remote Pacific Islands. I'm here to talk about science. I'm here to talk about one of the most fascinating subjects, I think, in the scientific arena, and that is the field of climate physics. What is climate physics? Well, the climate system has many different components. We have the atmosphere, we have the ocean, land, we have the Greenland ice sheet, the Antarctic ice sheet, the biosphere on land, the biosphere in the ocean, and all of them interact. They generate, through this interaction, a rich variety of temporal variability. Some of these events, some of these temporal changes are known to all of us, such as ice ages, which have a cycle of about 100,000 years. Another important climate phenomenon that is generated through this interaction between atmosphere and ocean is the El Niño Southern Oscillation phenomenon. And here in South Korea, of course, we are very familiar with the East Asian summer monsoon called Changma, which changes every year. Some years we have a strong Changma, some years we have a weak Changma. So all of these changes that we see in the climate system, many of them are generated internally through the interaction of the individual components of the climate system. In order to understand, decipher, and reconstruct the past changes of our climate system, climate physicists, they analyze ice cores, they analyze deposits from caves, for instance. They go out to the ocean to take large mud cores that will be analyzed to reconstruct past climate. But, as we all know, the natural cycles in our climate system are interrupted, are disrupted by our activities. Human fossil fuel burning is the main cause for several processes. One is, of course, global warming. CO2 that we release due to fossil fuel burning traps infrared radiation in our atmosphere, which warms the surface. But CO2 also partly gets absorbed by the ocean, where it causes a chemical reaction that is known as ocean acidification. And ocean acidification is quite severe. It is something that people call the second CO2 problem. It will affect marine life in our entire oceans. So that's something I will talk about later on. So we have the past, we monitor the present with aircrafts, with ground-based observations, with ships, with satellites. But how do we predict the future? Well, for that, climate physicists use some of the fastest computers in the world. And I will talk also about this today. Well, I wanted to talk briefly about adventures in science, and that comes back to terra incognita. So all of these possibilities to monitor, to reconstruct past climate using different types of climate archives, to use supercomputers, I was very fortunate in my career to be able to experience all of them. It started in 1996 when I was able to participate on a 10-week-long icebreaker cruise, research cruise to the Arctic Ocean. Over the last years, I was very fortunate to visit some of the most beautiful and really unique and remote places in the Pacific Islands to sample volcanic crater lakes and how they change their behavior over time. I was able to extract tree cores, 600-year-old tree cores from the upper slopes of Mauna Kea on the Big Island of Hawaii. And also recently, my team and we embarked on a monitoring campaign of limestone caves here in South Korea. So you can imagine nature reveals its secrets kind of reluctantly. But when it does, it's deeply gratifying and actually very often very adventurous. So one of these adventures, and talking about caves, I wanted to talk about the discovery process and the excitement. So what you're seeing here is just a piece of rock. It looks inconspicuous, and it is actually a cut stalagmite from a cave, which is nearly inaccessible, Jungmal Cave near Danyang. And you see some brown layers in there, nothing else. But however, if you apply the entire geochemical toolbox, you suddenly realize there is something absolutely amazing in this inconspicuous little piece of rock. So together with my team, we analyzed the trace elements and isotopes. This is work also done in collaboration with Gangwon National University. We analyzed these isotopes, and what we found is just remarkable. In this orange little time series, time goes from 19,000 years to 13,000 years, right to left. You see this very rapid event, and it turns out this is one of the most rapid climate events that was ever recorded in our planet. So this is illustrating a rapid climate reorganization that took place within essentially 10 to 30 years. And the interesting thing is that if we compare the data from our little piece of rock from a limestone cave near Danyang, if we compare it with caves elsewhere, such as in Spain, or if we compare it with sediment cores in the Mediterranean Sea, we can see the same event. There is something massive happening in the transition from glacial conditions around 20,000 years ago to interglacial conditions. And this is really one of the most remarkable climate change events, naturally occurring ones. Why did it occur? Well, our hypothesis was that a major burst of glacial freshwater entered the North Atlantic at that time and changed the circulation in the Atlantic, increased the ice cover in the North Atlantic, which in turn modified the atmospheric circulation in such a way that we can see these drastic changes in the entire planetary system, including South Korea and that little cave in Danyang, which recorded this event. So using actually supercomputer power, and we'll talk about it later, we were able to determine what would be the climatic response to a major freshwater burst into the North Atlantic. And what you're seeing is that the entire northern hemisphere becomes dry as a result of that. It becomes cold and dry. And in the bottom right-hand side, you can see the changes in the isotopic composition of water, actually the stuff that we directly measure from our spelotherm, even though it's calcite. And there we can see also there is a major reorganization in the atmospheric circulation. And if we compare our supercomputer model simulations with all the existing paleoclimate data, it is a perfect match. So our fingerprint, if you like, our paleo CSI really works. We have found a reasonable explanation for this massive event. Now, if the entire North Atlantic circulation can change so quickly and the entire Northern Hemisphere atmospheric circulation, we can ask the question, is that going to happen in future? How likely is it? How quickly is the Greenland ice sheet melting or the Antarctic ice sheet? Can they trigger similar events in future? Well, we hope not, but this is something that actually our team at the IBS Center for Climate Physics is analyzing in more detail. So what we have here is we are looking into the past, we are seeing events, we are learning lessons from the past for the future. Well, I said I wanted to talk also about dreams. Well, coming to South Korea enabled me to realize, to fulfill one of the dreams I had for a long time. Already doing my PhD in Germany, Hamburg, in the late 1990s, I was always dreaming of having more computer power. And you remember 20 years ago, the computers were clunky, slow, and so on. But it was always on my mind to get better computers in order to simulate the past, present, and future of the climate system more accurately. So coming to South Korea in 2017 started essentially this dream. And here you can see us in our first meetings where we discussed where are we going to install this computer. Our team and we designed actually the optimal configuration for a supercomputer. And eventually, with the help of the IBS headquarters, we purchased it. And nowadays, you can see our machine called Aleph in the IBS headquarters in Daejeon. Well, it turns out when it came online, it was one of the 500 fastest computers in the world. And it's still one of the fastest computers dedicated mostly to climate research, climate model simulations. It can do about 1.5 quadrillion calculations per second. So that's a 1.5 with 15 zeros. So that's quite remarkable. The storage capacity of this machine is equivalent to about 50,000 hard disks. So what can we do with this machine? Well, here you can see just a few animations. On the upper left, you can see simulated sea ice. So these are visualizations of the data. Data are just zeros and ones, but we can visualize them from these supercomputer model simulations, capturing the climate system under current or future conditions. So on the upper right, you can see, for instance, the simulated tropical cyclones or typhoons crashing into Japan and South Korea here. And so in these simulations, we can also change the atmospheric CO2 and figure out what would happen if mankind does not decide to go carbon neutral. And we can see major shifts in these tropical cyclones and their statistics. I can run it once more. On the lower right, you can see the atmospheric water vapor when the CO2 concentration in the atmosphere increases. So you see this massive red here, that indicates that we will have much more rainfall, also extreme rainfall in future. All of these things are simulated all at once in these supercomputer model simulations and many other processes and phenomena at the same time. So these model simulations allowed us to look in an unprecedented way into the past. We conducted the longest climate model simulation to date, which goes back all the way 2 million years to present day. We conducted the highest resolution climate model simulation ever for future climate change conditions, and I will some of these images are actually from this simulation. And we were able to simulate the climate probability distribution and how it changes with global warming at an unprecedented level of accuracy. So this tool, the Aleph supercomputer, really enables us to break the frontiers of climate research and do something that very few other centers in the world are able to do. So the results from these animations and simulations that you just saw, they were published in major journals, including Nature, Nature Climate Change, and Science Advances. And so for us, it is always important to really reach out to the general public and disseminate, explain our research results, and also get feedback and engage in a discourse and in a discussion with the general public. That's very important, I think, for climate research, because climate research is societally quite relevant. All right, well, I mentioned these results were published in good journals, and eventually the media picked them up internationally. Well, I mentioned also that we were able to do these extremely high-resolution simulations of future climate. And I'm just showing you some results here. What you're seeing is the temperature change relative to present day. The scale is shown at the bottom for the different months: January, April, June, and August. And you can see, well, our planet gets warmer if we increase the CO2 conditions over the next 80 years. And these pictures capture this temperature response to a CO2 doubling over the next 80 years approximately. And I hope very much that we can avoid this, that mankind is smart enough to dial down our fossil fuel burning to such a level that we can become carbon neutral very early in order to prevent such type of climate crisis. On the left, you can see the January warming on our planet in the next 80 years if we don't cut down CO2 emissions. And you see this massive warming over the entire Arctic area. You can also see that the Tibetan plateau, the high elevations, are warming up quite dramatically. Another interesting feature, and it's like a fingerprint, again, it's like this CSI story, climate CSI, the land is warming much faster than the ocean. Well, that is clear. The water can take up a lot of heat, which actually contributes also to the global sea level rise substantially. And then if we look at Korea, for instance, according to our computer model simulations, and we can zoom into much more regional details, areas such as Gyeonggi area or Jeollanam-do and so on, and figure out what are the regional aspects of this warming. But just over Korea in general, we will have about 4 degrees Celsius annual mean warming. And that, again, as you can see, depends a little bit on the month that you're looking at. But one of the key features that we can simulate now for the first time accurately is we have these mountains, for instance, the Himalayas. Global warming has an interesting feature. The higher you go up into the atmosphere, the stronger the effect of global warming will be. And that is something that you can see here in the Himalayas and the Tibetan plateau. You have additional warming. And that is very important because it leads to enhanced melting of glaciers in these high elevations, which can cause flooding, but also later on water shortage in a lot of the areas that rely on the meltwater from the snow. Well, this is what our planet might look like if we don't act. Then I mentioned there is another problem, the second CO2 problem. We blast CO2 into the atmosphere due to fossil fuel burning. Right now, about 30% is being taken up by the oceans, 25 to 30%, where it causes a chemical reaction. Well, what is the chemical reaction? CO2 entering the ocean reacts with carbonate ions to form bicarbonate ions. It sounds a bit boring, but actually it's a very dramatic shift. Because these carbonate ions that are there naturally, they are one component in a calcification process. So a lot of marine animals and plants, they form calcium carbonate shells to protect themselves, and we all know this, and skeletons such as corals. Now, you have calcium ion, you have carbonate ion. Normally, they can come together and they essentially form calcite or aragonite, the two different types of marine calcifying organisms. However, if the carbonate is taken out of the equation, then there is not much possibility to form calcium carbonate anymore in future. And that is a process that is not due to global warming, it is due to the CO2. It's a chemical process. Now, what we see here is in the upper left, 1850, there is an area that is green, which means this is an area where lots of the organisms in the ocean can calcify easily, no problem. If you go a little bit more to the Arctic, the calcification will be slower and so on. But as we increase the atmospheric CO2 concentrations, following a so-called SSP 370 scenario over the next 80 years, we will see that this zone, and I indicated it here, that this zone actually where calcification becomes slow to impossible, this zone moves all the way from the Arctic to south of Korea, which means in future, many of the calcifying organisms in Korea will not be able chemically to have this reaction that allows them to build their tests and shells. So this is crucial because it affects the basis of our marine food chain. And this is something that we should always keep in mind. Fossil fuel burning, the problem is not only global warming and sea level rise, but it is also ocean acidification, which messes up the entire marine food chain in our planet. Okay, so I mentioned, and you can see from these discussions, climate science is actionable science. It is socially, and politically relevant. So scientists from our center hence play important roles in international and domestic panels, such as Junie Lee from our center. She was the coordinating lead author on the UN's Intergovernmental Panel on Climate Change, 6th Assessment Report, Working Group 1. Professor Kyung-Ja Ha from our center, she is a member of the Presidential Advisory Council on Science and Technology here in Korea. So we have this relevance that we would like to bring back to the general public. And our goal is to provide really the best possible science for improving decision-making regarding climate change adaptation and carbon neutrality. Well, this is us right now, the IBS Center for Climate Physics, and we're all excited to work together in order to explore new scientific frontiers, but also to make a contribution to improving our planet through science. I wanted to close very briefly with some final words. Well, as a scientist, you struggle with enemies, and either on a personal level or at university level or scientific community level or society at large. And for me, the biggest enemies actually of scientific discovery and progress are pride, could be personal, could be societal, ambition, fear, power, and irrationalism. And we all have to stay firm and continue with our pursuit of scientific truth, scientific discovery, irrespective of these irrational elements that we encounter. And with that, I would like to highlight three of my mentors in the past that gave me some words of advice. Don't trust common wisdom. My mentor, Lothar Weiss, Richard Weiner, don't be a follower, be a pioneer. Professor Klaus Hasselmann, take risks, don't stay in your comfort zone. So with that, I would like to show you this figure, which actually came out of a computer model simulation that we conducted a year ago. And it shows the data, temperature, and the wind speed. And it shows something, a tropical cyclone, right between China, Japan, and Korea in this triangle. And those of you who follow the weather news, you will realize this cyclone looks very, very similar to the current conditions that we have Chandu. But also our research demonstrates that these extreme tropical cyclones will become stronger in future. And this is something to watch out. Right now, Jeju is experiencing already extreme weather. These things will change in future. So if we have a weather system, think about climate change changing, putting these weather systems more on steroids, if you like. With that, I would like to thank you for your attention.
네, 팀버만
Thank you, Director Timmerman, for such an excellent lecture. I'd like to thank you, Dr. Timmerman, on behalf of all the viewers. Now, let me invite the second speaker, Professor Cha Mi-young, who is the CI of the Data Science Group of the Institute for Basic Science. Professor Cha Mi-young is an associate professor in the Department of Computer Science at KAIST, and her papers on her fake news, poverty prediction, and abnormal transaction detection have been cited for more than 16,000 times. And she was the first Asian who was listed as the most influential as data science, and she served as a guest professor for data science team at Facebook's US headquarters. So please welcome Professor Cha Mi-young. Ladies and gentlemen, it is nice to meet you. I am truly honored to be here with such renowned professors and other directors, and I'm glad to see you even online. I'd like to begin my presentation by a question. Airbnb, Tesla, Kakao Bank, and Yanulja. What are the common points of these companies? They converted existing industries into digital, thereby writing a new future. Based on their success, there is a data science, which is my subject of research. So I'd like to talk about data science. So if you want to pursue this industry, then please listen carefully. I am currently working on data science. I'm leading the data science team at KAIST and IBS. I'm working with all these colleagues who look amazing. We have so many members of different backgrounds in my group: AI, computing science, electronics, machines, economics, media, information. They have all these different backgrounds, and they deal with big data in a freely. So if you just hear the name of the companies, we work with Facebook, Wikimedia, and UN organizations. So we conduct research on a global stage. Based on our experiences and my experiences, I'd like to tell you about real fun data science.
데이터 과학의
The vision of data science is the heterogeneous data. And by combining these heterogeneous, we have new creativity, and that's the basis of the data science. In the picture, you can see all the telephone or internet patterns on our planet. So this computing pattern and pattern of communication can be combined with the geographic information, which is heterogeneous data. Then we can come up with a research on trade relations between different countries or the lack of communications by different regions. And one of the successful case of the data science is the revision of Korea's Seoul's bus route map. Night bus was requested for revision for a long time. So how did the Seoul Metropolitan Government resolve this issue? The regional government wanted to know the demand for bus route for different times, so they cooperated with the KT because the bus has to communicate with the communication network. So, for instance, on Friday night, if you're working in Gangnam area and you want to move to the north part of the Seoul, then you can look into this data to know how many populations are using this route. So, based on this information, we can create a more convenient bus route. So, this is based on the combination of heterogeneous data. In addition, we can just see how the network pattern changes, and we can get a lot of information. On this picture, you can see that social network pattern is changing. Out of so many couples these days, we can predict after 6 months how many of those couples would still remain as couples. So this is a result of our research. In the future, the text messages at the appropriate timing and even the content of a message can be supported by AI, and you can even make a judgment whether or not this is a good sign for your dating scene. Actually, we do have that kind of app already. Maybe it seems like a far future, but if you see the statistics from last year in the US, the number of couples who met online and got married account for 22% of all the married couples. So you can try out the AI-supported algorithm for your dating, then it would be great help. I'd like to give you a few examples of our research. We collaborated with a UN organization for food issue. We took interest in Indonesia. There are over 10,000 islands in Indonesia, and people live in 10,000 islands, and they rank fourth in terms of the number of population, and many of them are in a food shortage. So it takes a long time, and it's very difficult to predict the price of foods in such a difficult situation. So we predicted the prices of pepper, chicken or beef or other major food items on a daily basis. So we developed a nowcasting algorithm, and we provide this to the UN for free. The algorithm that we created was 10 days faster than the existing statistics. So it would tell people how to make investment or what kind of food items they have to purchase in advance. So it was a very useful algorithm. Our group also used big data to detect fake news. So we were a globally leading group when it comes to detection of fake news. Can you detect fake news from this video? You can see on the left-hand side, you can see different dots, and dots mean people, and you can see the connection between people that follow link in line. And if you see on the left side, you can see the formation of dot, and it's very dispersed, which is fake news. On the right-hand side, you can see a real news, and you can see that people are connected as the news is dispersed and spread. So you can see big, large-sized connectivity and components. So when it comes to the pattern of spread, the fake news is different. So if this is learned through deep learning, then up to 80 to 90% of the cases, you can tell if it's a fake news or a true, real news. Some of the scientists in our group are working as a scientist for change. When it comes to the international trade, we are helping them to catch those who violate the customs regulations. The customs officials have their own know-how, and they have their own accumulated information information. So they would create the customs algorithms so that they would know a certain product would be illegal product. So that was a bit simple algorithm they were using. We changed this into deep learning algorithm, and we are still doing it. And we also have a smart algorithm that we are developing that would explain why this is illegal. So the custom officials would only have to inspect a few number of products that would be selected by the algorithm. And this is of a great help, especially in the current COVID-19 situation. During the COVID-19 crisis, there were a lot of fake news. Our data science group, in the initial stage of COVID-19 crisis, which was March, April last year, we launched a campaign called Fact Before Rumors. In this campaign, we looked into the rumors that were dispersed in Korea and in China, and we changed into these rumors into facts, and we uploaded infographics based on these facts. And this infographic was translated into 24 languages. So this information was delivered to about 50,000 population in the world. The World Health Organization actually invited us as they selected this as the excellent case, so we gave a presentation at WHO. So our scientists do not just do a research. Our scientists actually are very active in terms of promoting this as a real help for the people. We also have experts in image analysis, so those analytics are creating technology for satellite image. They were geologists or economists or physicians. They all do they would allow all these physicians or geologists who couldn't really analyze these images. On the left-hand side, for instance, you can see the image of islands that you can reach, or North Korea that you cannot go. And these regions can be analyzed by region in detail only based on the satellite 3D image. And we can even abstract the economic indices as well. On the right-hand side, you can see how we can calculate the amount of green areas in cities based on satellite images, and we can calculate based on these images how much of these green areas would contribute to the happiness of the citizens. We are also doing some of the social contribution campaigns. This campaign was actually organized with psychologists together. During the COVID-19 crisis, the sleeping pattern and living pattern of elementary school students were collapsed, we thought. So we wanted to share some tips from middle school students or high school students through app, and we wanted to distribute this through the app. So we are planning a 14-day challenge for children. So if you're interested, you can come onto the link below, and you can find the information on how to join us for the campaign.
저희가 하고
So up to now, I've introduced all the different areas of research that we are doing. I believe the digital conversion of existing industry will be accelerated, and data scientists will have a bigger role in terms of in our society and in policies and in different industries as well.
어떻게 하면 이제
Then, how can you become a globally renowned data scientist? I worked at Facebook in Silicon Valley, and I also worked with the world-class data scientists in different organizations around the globe. And I've heard, and I've seen how they work. So I'd like to share my tips on that.
자, 제가 근무했던 이제
This is a banner that you can see on the road of the Facebook where I used to work. You can see the name of the street, and you can see Facebook as well. On the other side of this Facebook banner,
회사의 이름이 그대로 써 있.
You can see the name of the company that used to be there before Facebook. Why did the Facebook just still use the banner of the company that was there before, to have the mindset that they may be kicked out from that site any time? The scientists do not mind too much about the current or present success. They truly love their research.
현재에 매달리고
This is the first mindset that they have, which is do not stay complacent for now. You can see the face of Mark Zuckerberg. He's the CEO of Facebook. He's always wearing great T-shirts. Why? At a town hall meeting, someone asked him why, and he answered to the question when he was asked why he's always wearing a gray T-shirt, and he said, the small decisions such as what to wear, what to eat every morning, I don't want to waste my energy to that. So he knows what's really important. He wants to completely dedicate it to that. That's the choice that he made. I think that's the second secret. The last secret I found is that when I first started working at Facebook, when I first joined Facebook, I thought that this is a social app company gaining profit from advertisement. But when I saw the organization chart and when I meet people working there, I realized that they create a device for virtual communication, and they are doing brain science research. And they are doing a drone research for free drones in a developing countries. So there are a lot of different types of researches being done, and social app was only a small portion of that. But many other companies that I've seen were actually very similar. The largest search engine, Google, in the world is only a part of the alphabet G out of the entire alphabet, because the Google itself has so many different businesses or research areas that they're doing. So Facebook, for instance, has a mission to connect people all around the world. So in all areas that meet that mission, they are doing different types of research at a different level. So that's the last secret that the worldly renowned data scientists have. So when I talk to these people, they are so famous globally, but they're so humble, but so visionary people, and they continuously expand themselves, and they're continuously learning. And they have great capability handling the data, and they want to use that ability to resolve the issues such as climate, poverty, shortage of food. And whilst addressing all these difficult challenges, they would see opportunities. That could be Tesla, or it could be Kakao Bank. I have a phrase here that I'd like to share with you. What would you do if you weren't afraid? If you are not afraid, and if you know the end result is a success, then what would you analyze right now, and what would you try right now? Based on this phrase, I'd like to wrap up my presentation. Thank you very much. Thank you very much, Professor Cha Mi-young, for your insightful lecture. Now I'd like to invite the last speaker, Hyun Tae-kwan, head of the Nanoparticle Research Center at the Institute for Basic Science. He is currently in the US, so he is joining us online. Director Hyun-taek Kwan joined the Department of Chemical and Biological Engineering at Seoul National University in 1997, and for around 20 years since then, he has been conducting research on the synthesis and application of nanostructured materials. He is currently leading the nanoparticles group at IBS, and he has published more than 400 academic papers. And in 2011, he was ranked 37th on the list of the world's top 100 chemists, and he was also selected as the possible candidate for a Nobel Prize. Now we will hear from Hyun-taek Kwan.
만나뵙겠습니다. 반갑습니다.
Ladies and gentlemen, good morning. As I've been introduced, I am Hyun-taek Kwan. Currently, I am a professor of chemical and biological engineering at SNU, and I'm the director of the IBS Center for Nanoparticles Research. Today, I would like to present to you one of the research projects, one of the most important research projects that I've done in my past career of 30 years, which is the development of monodisperse nanoparticles. So in the earlier presentation, Mi-young-cha talked about Zuckerberg and the episode. I heard about that episode as well. He wears the same clothes every day. And when someone asked him, why do you always wear the same clothes every day? And Zuckerberg apparently answered that he doesn't want to waste time on unnecessary decisions, unnecessary daily decisions. And I think these trivial daily decisions and also major life decisions like who to get married with, I think life is a series of both small and big decisions. That's how I would define a life. And when I look back on my own life, especially on my life as a scientist and as a researcher, looking back on my past 30 years, I think, what were the major decisions of my life? And I think one of the major decisions was in 1997 when I became a professor at SNU. At the time, I got my PhD degree in the States, and if I researched the same thing as a professor at SNU as I did in the States, then it would have been easier for me. However, I didn't want to do that, and I made the big decision to jump into the new domain of nanoparticles. It was a completely new domain for me, and I decided to jump into that domain, and that big decision made me who I am today. I think nanoparticles can be defined as a technology that supports other domains, such as semiconductors or anti-cancer treatments or cancer diagnosis technologies. Or, as you know, Pfizer was developed as an mRNA vaccine, and so was Moderna. And these vaccines are basically the key to solving the pandemic. And whenever we hit technological barriers, nanoparticles can support you and help you overcome the obstacles. And so in the 21st century, nanoparticle is something that can be helpful for any domain, any technology. And nanoparticle has various applications in diverse fields. And to apply nanoparticles, you basically need 2 to 5 nanometer big nanoparticles, which already have a lot of applications. And that is how I would describe nanoparticles. Which of these do you think look better? On the right, you see everything is all mixed up and cluttered. On the left, everything looks even and same-sized. Now, with nanoparticles, having even-sized nanoparticles, they don't just look nice, but also it's very important to have even-sized nanoparticles. Why? Because the size of the particles determines the properties of the particles. Quantum television is actually using this technology. So as I said, the size of the particles determine the properties of the properties. Nanoparticles in semiconductors are obviously very small in size, and when you shed light on the semiconductor, the UV light, then you would see the rainbow color. And the fluorescent color of the nanoparticle is determined by the size of the particle. So that's what happens in a semiconductor. So if you make, for example, all 5 nanometer nanoparticle semiconductor, you get a red color. If you make it a smaller nanoparticle, if you use a smaller size nanoparticles for the semiconductor, you would see a green color. If you make it even smaller, you would see the blue color. Why do we need to make it even sized? Because you need to get clear colors, vibrant colors. For example, if you get particles all of the same size, for example, 3.4 nanometer, you would see a vibrant green color. However, if you use different sizes, then you wouldn't see a clear color, a definitive color anymore. And the person who first did this research was a researcher in MIT. And as you can see, this diagram shows that all the nanoparticles are even sized and regular. So I think this slide summarizes the research, or any research that great scientists do. What we first do is we have to read all the literatures to find out what other research has been done by other scientists in the past. So you have to read the review articles of the recent review articles of the top journals. And while you read the articles, you have to identify what are the issues that have not been addressed yet. What are the important issues that have not been addressed yet? And then you can basically identify the research topic for yourself. You have to resolve and address the issues. That is the purpose of the research, and that is what the great scientists have been doing for a long time. And that is what I do as well. So going back to the nanoparticle research project that was conducted at MIT, as you can see, what we want is even-sized monodispersed nanoparticles. And you cannot do that right away. When you make nanoparticles, they come in many different sizes. So you have a mix of so many different sizes. And that's an easier way to make nanoparticles. So you first make nanoparticles with many different sizes. Do you know how small 1 nanometer is? It's 1 billionth of a meter. So you can basically imagine how small that is. You know how it's difficult to grasp 1 strand of hair? 1 nanometer is about 1/10,000 size of a strand of hair. And you have many different nanometers that are mixed with each other. So it's very difficult to separate them into the same sizes. However, if you use this process developed by MIT, you can actually separate the different sizes. Now, before this research, they didn't have a way to do so. And so we came up with a way to solve this issue. We came up with ways to actually synthesize monodispersed nanoparticles without size separation, because the MIT research had to go through multiple processes to actually separate the sizes. But we came up with the way to synthesize monodispersed nanoparticles without size separation. And in 2001, we published this article in a very important and renowned scientific journal. Also, this was published in the Science journal, which you must be all familiar with. And what we did was, First of all, we wanted to synthesize monodispersed nanoparticles without size separation. And we published this in the journal. This was one of the very important articles that were ever published in this domain. However, there was a problem. The problem was what we used in this method uses a very expensive and very toxic substance, as you see on the slide. As you know, CO, carbonate, is very toxic, and when you combine it with Fe, of course, it's going to be more toxic and more expensive. And that was the problem in our research, and we had to overcome that problem in the research. We had to find some other chemical that was safer and cheaper to synthesize monodispersed nanoparticles without size separation. So we wanted the most safe and the most affordable metal to create this new chemical. And using this, we were able to lower the price by 10,000 times and also increase the yield by 1,000 times. So because size separation of nanoparticles is so important, we were able to then use this chemical to basically create monodispersed particles at a much lower price.
So that's how we created this. So this was cited for more than 4,000 times based on Google Scholars. So it was the representative papers that was cited a lot. So CNN was also introducing us. What's important was that in 2006, in the material science area, there are so many thousands of papers, and we were selected as the most cited paper. So all of these technologies, especially at the engineering department, the research, of course, it's good. It's important to produce good research results, but you have to secure the patent. That's the most important thing. So we also secured a patent. So Hana Chemicals main research lab made such an effort. So now you can mass produce the monodispersed particles, and this is being used by many different industrial sites and also many different research institutes. They are following exactly same technologies, but they are also developing developing different technologies based on that, but their main source technology is our technology. So that's one of the major technologies that we had. In the past 20 years, around the time, actually at the time when I was appointed as a professor, nanotechnology was beginning to develop in full force, and the White House in the US first started to sponsor the nanotechnology in 1999. So 2019 celebrated 20th anniversary since the beginning of the nanotechnology. So Nature Nanotech, which is a representative journal, looked back on the most representative research achievements of the past 20 years, and they selected the quantum dot enhanced television as the most representative technology. And all of these technology became possible because, well, this is Professor Chang Eun-ju at the Samsung Electronics Materials, and this is the materials and images that she provided to me. The most important part of the Samsung's television is actually this technology. The QD enhanced television. In developing this television, the most important thing is also monodispersed nanoparticles. Also, the quantum dot enhanced television created by Samsung Electronics used the mass production of quantum dot. So mass production is extremely important here. The first, this result was first reported by the French research paper that was on synthesis, master synthesis of quantum dot. So you can see Hyun T, which is my name. So this was based on my paper. You can see that from here. So last year at the Nobel Prize, it was introduced by the announcer earlier, but it's same for this year as well. Who are the candidates, possible candidates for a Nobel Prize? And one of the important qualification and criteria is a citation. So MIT's Munji Bawendi and his first student, Christopher Murray, and I, so 3 of us were actually selected as the laureates. In the scientific history, there are about two miraculous years. The first miraculous year is 1905. The situation at the time in terms of the industry is very similar. Isaac Newton was actually attending Cambridge University at the time. He was at home and he was doing a lot of research, and he discovered a famous law, which is universal gravitation. He also discovered that there are 7 colors in rainbow. Also, he conducted a lot of different researches. So that was in 1905, which is a year of miracles, a miraculous year of Einstein, because the special relativity was actually discovered this year. Also, the photoelectric effect and Brownian motion, or E equals mc2. So all of these, the 4 major principles, or the papers on these principles, were announced in the European Physics Academia. And I believe that last year was the year of miracle for me, because in 2002, January 16th, Professor Alektasis and I, we announced a paper which was the cover of Nature. And also, we announced another paper about the nanosensor. Also, we developed another nanoparticle-related paper on the monitoring of diseases, and this was also the main paper of the science paper as well. But there is a major difference. The miraculous year of Einstein was 1905. As you can see, there were 4 major papers, and you can see that the author is by Einstein, so there was only 1 author. But for the papers that I produced, or we produced, there were 15 authors for the Nature paper. And you can see the UC Berkeley professors, 2 of them, and the Seoul National University's professor, and the professor from Stanford University. So there were 7 professors involved. So many people were involved. In the beginning of 20th century, not just Einstein, but Schrödinger, Curie, or Heidegger. So this genius scientist would resolve issues, problems. In the 21st century, these issues are complicated, so we need many different scientists or researchers who have to work together to resolve these issues. Our research motto is to come up with ideas and collaborate with each other, not working alone. So we want to work together, and we want to provide some helps for people to eat and live well. So these are my students who supported me to achieve these results. So I did a lot of co-research with so many people. So thanks to the IBS, I was able to conduct a lot of different researches in the past 10 years. So thank you very much for your attention. Thank you. Thank you very much, Director Hyun-taek Kwan, for such an useful lecture. I'd like to express my deepest gratitude to the 3 speakers who put together great session. So this concludes the Open Session Science Concert. I'd like to thank all the online viewers for staying with us until the end. Thank you very much.